variance, of the true variance, and it's not really the true variance, but the variance, but it is scaled by these elements in Mx. So this is why it says then under here the note that although usually the variance of u would be sigma squared I, which is our assumption, but we don't observe this. So in finite samples, the residuals don't have a constant variance, because maybe I can write this out here, the variance one, the matrix ones. So how does Mx look like? Well, we have first, this is also sigma squared times I minus Px. So that's the definition of Mx. So we have here a sigma squared, and then on the main diagonals we have 1 minus Pii, or here in this case they call it Hi, which is the leverage which we discussed I think 2 weeks ago. Right, so this is always on the main diagonal. This is an H1, H2. And so on to Hn. And then on the off-diagonal elements, they're not so important because those are the covariances. We're thinking about the variances right now. So what we have here is that the true variance is actually scaled with 1 minus H1, which is smaller than 1, right? So we know that H is between 0 and 1, so 1 minus H1 is larger than 0, but smaller than 1. So what's happening here is that we downscale the sigma squared. Right, so this here is going to be smaller than this. And what's also the case is that for each residual the variance is different. Right, so other than so it's not like the variance of u, where we assume that all of them have the same variance sigma squared and they're uncorrelated because all of the off-diagonal elements are 0, right? So there's no covariance between the true errors, but for the residuals, we actually get variances that vary from residual to residual, and they're governed by how large the leverage is. So the higher the leverage, the smaller the variance. And then also the off-diagonal elements, these are not 0, right? So here we have a value which is M12 to M1n, right? So this is what they mean by they're correlated here. They're correlated in the constant variance. And the leverage is important because it tells us how much the variance of the residuals diverge from the true error variance. Okay? Any questions for this slide? Okay, then let me go to the next. So now we establish this relationship, what the variance of the residuals are, and it has this relationship with the true variance, right? So we can also maybe factor this out one more time. So we get the variance times I minus sigma squared px. And you see this would be the variance of u. And then the variance, we subtract something, which is positive definite. We could show that px is positive definite. So we subtract something. So the variance of the sigma of the residuals is actually smaller than the variance. And what that means is that it systematically underestimates if we would just take the variance of the residuals digits as is, we would systematically underestimate the variance of the true error. Right? So the variance of the residuals give us less variation than actually is an error. Okay, and now in the next slide, what we do with this, and here you see again the whole thing, what I just wrote down, right? So that the individual variances of the residuals is this product of the main diagonal elements of mx, which is 1 minus the leverage, times the sigma squared, which is smaller than the respective variance of ui. Okay? And now, yeah, we try the moment estimator, where we just plug in the sample moment for the variance, which is the sum, the average of the sum of the squared residuals. Yeah. And then things are plugged in. Any questions here? What's going on? To then get the variance, to get this thing here. Yeah, but the problem is, why do we do this? Well, because, okay, so this is always a good starting point to just try the moment estimator and then calculate if that is unbiased. Because in a lot of cases, the moment estimators are already going to be unbiased, right? And now, we plug this thing in here into the calculate the expected value, right? And now we know that here, this is the variance of ui hat of the residuals. So we plug this thing in here, and then we have the sum over sigma squared times this, okay? And that is also the trace of, because that's the sum of all of the main diagonal elements, that's actually the trace of sigma squared mx, which is the trace of sigma squared 1 I minus px I minus px, and now we know, yeah. And this helps us to tell, I mean, the question becomes where does this n minus k come from, right? So we know that the sum here is the trace of the main diagonal elements, so then we have sigma squared, which we can take out of the trace, because it's just a in each a factor in each of the main diagonal elements, we can just factor it out. So we're left with the trace of I minus px, and we have sigma squared times the trace of I minus the trace of px. And now we know that this I here is an identity matrix with order n. So we get the trace of the identity matrix is n, and the trace of px, we already showed that this is k. If you remember from, I think, 2 weeks ago. Is it? So we have this n minus k here. So we see that the n minus k is, and n doesn't cancel out, so this would be a biased estimator, right? So this is biased. And it's downward biased, because n minus k is smaller than n, so we multiply with something that is smaller than 1, that is between 0 and 1, so we get something that is downward biased. why we then just, and that's the easiest part, we know now because we have this n minus k in the numerator that we need the n minus k also in the denominator, and then we know that we need to switch out the 1 over n in the mean here in the expected value with 1 over n minus k. This happens. And did that answer your question, or did it confuse you more? Okay. And this estimator of the variance is actually kind of interesting to show because this shows that sometimes we can just try out also estimators, right? So it's not like a derivation the same as with the OLS estimator where that is the result of some minimization problem, but this is more, and this can also work, okay, we know that this moment estimator thing exists where that is super simple, where we just switch out theoretical and empirical moments, and then we can just check the properties of this moment estimator, and that's going to give us more information on how the estimator should actually look like, right? So because this moment estimator, which we could always use when we want, which we could always use, this gives us the information on how to create the actually unbiased estimator. Because while showing that the moment estimator is biased, we see with the factor, this factor n minus k, which we actually need to divide by. Okay. Yeah, by looking, so this is kind of a way to, maybe another way, the bias of one estimator can help us finding an unbiased estimator for the same thing, right? Because we want something that cancels out this bias that we have, and the bias here is governed by this factor n minus k over n. Any questions for this? I would really recommend you guys to try to write it down on a paper, not only with the lecture slides, because sometimes it helps to also rearrange maybe the order in which you do things to help your brain think about what's going on there. Okay. So, if there are no more questions for this, then let's, yeah?
Could you please explain one more time about the trace?
Yeah, so the trace is the sum of the main diagonal elements of a matrix. So if you have a matrix A, which is with the main diagonal A11 to ANN, and off-diagonal elements don't matter, then the trace of A is just the sum over all of the elements and the main diagonal. Yeah, that's just the definition. And this is why we see that that we can actually use the trace here, or that we need that we can actually use the trace here, because this here is the sum, and these are all of the main diagonal elements of this matrix. Right, so this is the diagonal of the sigma squared mx. covariance matrix gives us the variances, and this is where what we need here. So the trace gives us a nice way to get at only the sum of the variances, because that is the definition. Okay. Then if there are no questions for this, then let's jump to the Gauss-Markov theorem, where we show that if we have strict exogeneity and the error variance is sigma squared I, and the true model is y is equal to x beta plus u, the OLS estimator exists. The OLS estimator is the best linear unbiased estimator. So it's in the group of linear unbiased estimators, has it's the most efficient. So it has the smallest variance, smallest mean squared error. Yeah. And this is the proof. We saw it in the lecture. I don't want to, and the aim was to not go through the whole thing again, but any questions for any of the steps? Can recap. Because sigma squared is a scalar, and scalar multiplication so it's just a value, so that's 2. And this is the one thing in matrix, with matrices, the scalars you can always put it from, because it doesn't matter. A scalar multiplication doesn't really multiply everything in the matrix with the same value. This is what, it's kind of we factor out something that is in each and every element of the matrix. And we can always pull that up from. Another question. Yeah, then I have a question, but I just want to get an idea. If you don't have any questions because it's all clear, or it's not all clear. Okay, so you don't have any questions because you don't understand it well enough to have questions. That's the point. Okay. So maybe then let's at least go. I think the idea of this proof is pretty straightforward. So because we want to show that the OLS estimator is the best linear unbiased estimator, we need any other linear unbiased estimator to compare it to, right? Because so that we can show that it's always going to be always going to have the smaller variance. So the first thing that we do here is define this other linear unbiased estimator. And this is the beta tilde, which is just a y. Right? So this a is just any linear combination of y that gives us this. So this is already this is a linear estimator. And we say, oh, this also has to be unbiased. So the expected value of beta tilde is beta. Okay? And then the same as we did when we showed the unbiasedness of the OLS estimator, we write this beta tilde in terms of the true value and the error, right? So that we can calculate the expected value of this beta tilde, and then we see that for this to be unbiased, the relationship A and X has to be in a way that A is the identity matrix. AX is the identity matrix. Okay? First thing. So for this thing to be unbiased, we need this relationship here. AX is equal to I. And then let's jump just a moment down here for the variance. Now the question is, what is the variance of this unbiased, linear unbiased estimator of this AI, A times Y, right? So we again plug in the true model, which is done here very, very quickly. So this step is very quick, but this is just the variance of A times U. You could also think about it, well, we know that the variance of our dependent variable y is governed only by the variance of the error and not by the variances of all the residuals, so of all the regressors x. So we're just left with this calculated, and then we have here, this is the variance of the estimator, of the other linear unbiased estimator, sigma squared A prime. Right? And now the question is, how do we compare OLS, the OLS estimator? Where's my the variance of the OLS estimator, which is sigma squared x prime x inverse. This is the variance of the OLS estimator, right? How would we compare this if there are no similar matrices? So here we have the x's, here we have something with A. I mean, we know something about A and X, but how do we compare this? Well, we produce this nice matrix D, which gives us the relationship between the matrix A and the matrix X, so that we then can compare. So the D is just defined as the difference between A and this thing here. Right? And why all that? Well, so that in the end, the aim is to get the variance of beta tilde as the sum of something and the OLS estimator, the variance of the OLS estimator. Right, so this is here. That's in the end, this is the variance of the OLS estimator. So this is where we want to get. The D is defined in this way, and we also know that for this whole thing to work, D times X has to be 0. So this is another specification of how this follows from the definition of D. Okay? Because if you just plug in A, if you just calculate this dx, then we see that this is A minus x prime x inverse x prime times x. So this is A times x, which minus x prime x inverse x prime x. We know that this is the identity matrix. We know that this is the identity matrix, so the result is 0. So this just follows from AX is equal to the identity matrix, which follows from that we need an unbiased estimator, right? So AX equal to I is defined in this way so that we have an unbiased estimator, and then this AX is equal to I also gives us that this dx thing is the dx thing is 0, and the d, we need that to get this relationship between the variance of the linear unbiased estimator and the OLS estimator. And this here, that stuff is just annoying linear algebra. Where you can now ask questions. What's going on? Yeah.
But like, where is the D coming from?
Yeah, I mean it's defined. Let me for just a moment check my, because I do that. This is, I read it out of it. yd. So that comes from the relationship between the OLS estimator, the linear estimator, which is a times y. So the thing is, we want to write this OLS, because we want to compare the variances of the two, right? We want to be able to write the beta tilde in terms of beta hat. So we did this before, right? So writing, because we need the relationship between residuals and error, we need to plug in the true model so that we can see this relationship clearly. We do something very, we actually do the same thing here. We want a relationship between beta tilde and beta hat. So what we need for this is to multiply, ask ourselves, well, the beta hat we know is x prime x inverse x prime y. Okay? Right? So this is the thing. This is beta hat. And then obviously there has to be something else, right? Because beta tilde is not beta hat by definition, right? So there has to be something else. So we can and this something else, the A also is not there. We also don't know how A looks like, right? So A is just the matrix that makes this a linear estimator. And now we just say, well, let's think. Like this, let's think, well, just another matrix so that the sum of the matrix D times Y and the OLS estimator gives you this linear unbiased estimator. So this is really just a helpful little matrix that gives us this relationship. And right now we don't have any idea how this looks like. Right? So this is how this is, and then we can factor out y. So then we know that a times y is this, and now we know that a has to be equal to d plus x prime x inverse x prime, and then we know that d is a minus x prime x inverse x prime, right? And both these matrices A and D are just there to help us get this relationship between beta tilde, between a linear unbiased estimator and the OLS estimator. Any questions for this? Let's go back. Yeah, these steps here is really multiplying out fragments and calculating matrices. It's just important I mean, the important matrix rules that you need to keep in mind to be able to do this is that there's a transpose here, so you need to switch around the order of things, which is how this d prime becomes a thing. Then another thing that you need to know is that I mean, this here is by construction 0, right? So dx was 0, and then you just need to see, or you need that this thing here is just the transpose of dx, and the transpose of the 0 is also 0. So that's kind of the matrix things that get where those things might get a little bit tricky, or where you might make a mistake with the matrix algebra because the transposes, but other than that, it's multiplying out these brackets, and then you get all of the different terms. Yeah. And then because dx is equal to 0, this here drops out, and we just have the rest. And then we see that this here is the identity matrix. Yeah. So I think to practice matrix algebra, this is actually nice to write it out once. Okay. Any other questions? Okay. And then, so what we have now at this point is this relationship between the variance of beta tilde and the variance of beta hat. And now, and the difference of both is the sigma squared d prime d. And sigma squared is always positive because it's a squared scalar. So the question becomes, what is d prime d? How, what is it that's supposed to be? Well, and now we can show that this is actually this difference between the two error variances, the difference between these two variances of the two estimators is actually positive definite for all A, which is defined as that this quadratic form of the matrix is always positive. And at this point, Professor Niles, I think, picked up somewhere here, I don't know what he actually did, when he did this, but I know that he left off here and with this slide at this point and talked about the definiteness and how to check actually and how to see if the matrix is positive definite. And one of the nice things is that the matrix is always positive. One necessary condition for a matrix to be positive definite is that the main diagonal is positive, and then the off-diagonal elements are going to tell us if it's actually positive definite, because this is not a sufficient condition, but we can also check the eigenvalues, and this is where I left off, and now we can, if there are no questions, we can go and talk a little bit about eigenvalues, so that those don't fall out of the sky, just fall out of the sky here. That's kind of why we're going to talk about why I have the eigenvalue slides that I uploaded, so that this part makes sense, and you hopefully also get a better idea of why this is helpful when thinking about these variances and the difference between, yeah. Okay, questions for the Gauss-Markov theorem? Okay, then let's start with the eigenvalues. And I start with the simple definition, and then I hope that we can together look a little bit deeper and hopefully get what this is going to tell us and what these are, because that's actually like mathematically not so difficult. Okay, so if we have a square matrix A, then lambda, which is an element of the real number, so real number lambda is called an eigenvalue of this matrix A, if we find a vector x, which is not allowed to be the null vector, so not a non-zero vector x, that gives us this relationship that the A times x is equal to lambda times x. In this case, x would be the eigenvector and of A, and lambda the corresponding eigenvalue. So there's always this relationship between lambda and x, so between an eigenvector, eigenvalue and a vector. And what I think is very fascinating is that if we look at this, then this means that this matrix multiplication A times x, so a matrix, and this can be a big, very, very large matrix, right? So any matrix you can think of, this matrix A times x is the same as just having one scalar multiplied with x. So we get the same result multiplying a matrix, any matrix, any squared matrix with x, as we get when we just multiply this scalar lambda, which can be just a 2 or something, right? So that this works, that this whole, all of this, and I think about it a little bit like all of the information A, and everything A does to x can also just be done with this little value. So the eigenvalue lambda is actually a lot of information. That we get a lot of information from it. We know a lot of about the matrix A by looking at just one value lambda. So that it really doesn't matter what dimension this A has, other than that it has to be a square matrix. So let me just, because it's also an exercise, I want to use hopefully some examples. So the matrix that we saw on the last slide from Professor Naus was actually eigenvalues, which is 3 multiplied by that vector x. Okay? And later on, we can, if we want, calculate the eigenvectors, and I'm just taking it, going to tell you already, so that we're all on the same page. The eigenvector for the eigenvalue 3 would be 1, 1. So multiplying 1, 1 with the matrix, and this is a small matrix, but we can think of other examples, gives us the same result as just multiplying this vector by 3, because it's an this is the eigenvalue to that eigenvector. And also all of the multiples of the eigenvector. So we never only get, I think eigenvectors sometimes sounds a little bit misleading because we think about them one vector, but what we actually get is a whole set of eigenvectors, because each multiple of that eigenvector also, again, is an eigenvector. So we could also multiply just the vector 2, 2, and this would still work. This is the last slide, right? Like this, okay? And then we also have another eigenvalue, because that works for two different things. So we also get the eigenvector 1 minus 1. And the eigenvalue 1. Okay. So that's going to be the same. So let me just try to visualize this for a moment, so we get a better idea of what's going on. And for that, we can remember that vectors, we can write them in coordinate systems, right? So if you think about this one eigenvector that we just had, is the vector 1, 1. Right? So this was one of our eigenvectors. Then what the eigenvector and eigenvalues actually mean is that if we multiply this eigenvector by 3, which is just a stretching of this eigenvector by factor 3, so this purple is going to be 3 times eigenvector 1, 1, right? This is going to be the same as transforming this vector with the matrix A. And that's the case for all of the eigenvectors. Also, the other eigenvector, which was minus 1, 1, we can also, is also just stretched by the value 1 is the same as multiplying this matrix with the same vector, right? So the transformation that we get for this vector is, if it's an eigenvector, it's just that it stretches with a factor lambda. And in this case, because lambda is 1, it doesn't do anything at all, right? So I mean, that's kind of, if you have this is kind of the intuition of an eigenvector, eigenvalue 1, the matrix of eigenvalue 1 tells us that there's an eigenvector that isn't changed by this by the matrix at all, right? And that's true, right? So the stretchy thing, that this is just that the matrix just stretches this vector, is true for all values, for all vectors that is on the same line, that is on the span of this vector. Like all of these vectors on that line will be multiples of the eigenvector that I just drew. So the whole line, right, so the whole thing, all of those are eigenvectors, and all vectors that are on these lines are just stretched by the matrix. If we have any other vector, right, for example, this here, in this direction, this vector here, which is not an eigen, not on any of the eigenvector spans, 2 by 2 matrix, this one would rotate this vector. So the vector, if we multiply this vector x, this vector y, by the matrix A, it would, y, it would actually rotate it, right? So this A would rotate it so that we get this new vector that goes somewhere else. It stretches and rotates. It might stretch and rotate the whole thing. So rotates it this way and also stretches the vector, right? And the eigenvectors are great because they just kind of stay in place and are just stretched out. And the eigenvalue tells us how much it stretches out. Eigenvalue that is positive, like in our positive semi-definite matrices, they all have positive eigenvalues. The eigenvalue is positive. That tells us that it only stretches the vector in the same direction it already goes, right? So it's never going to flip it. If we have a negative eigenvalue, that would mean that the vector 1, 1 would become, just go in the other direction. Go down. And that's what you don't, that's not possible for positive definite values. Okay. Any questions? So that's just the mathematical thing of what the eigenvalues do. And now let's have a look at how to calculate them so that we can, that you can actually use this. And obviously when we're at home, we ask the computer because they can all calculate eigenvectors, but I think it's also good to know what's actually going on there. Oops. So the way we are going to calculate eigenvectors is actually by calculating the determinant by knowing or by calculating the determinant of this matrix and setting it to 0, because we know that the determinant of this matrix has to be 0, right? And then this determinant, this here, is going to give us an equation that we can solve for lambda, right? So this determinant, because it's a determinant that depends on lambda, and then we set it 0, so we can calculate the lambda. So that's actually what's going on mathematically. Why does this work? Well, first of all, we start at just with the actual definition of the eigenvalue, so Ax is equal to lambda x. Then we input the identity matrix here. Why do we do this? Because we want to, right now, the left-hand side is a matrix multiplication, and the right-hand side is a scalar multiplication. And we want to write the scalar multiplication in terms of a matrix multiplication, so that we can then take this matrix multiplication on the left-hand side, right? So that we get this next step where we know, okay, we subtract it here by lambda I x, get it on the other side, so we know that A minus lambda x is equal, in brackets, times x is equal to 0. Okay. So this is kind of where we left off, and now we need this little effect that we I don't think we talked about yet, but because we're searching at x which is unequal to 0, so if you look at this, then this is a linear system of equations, right? Each matrix times x can be and this is times is equal to 0. This is a linear system of equations, and this system of equation always has a trivial solution, right? So because this thing can always be 0 if the x is 0, right? So x is equal to 0, but we're searching for an eigenvector, and the eigenvector is not 0. An eigenvector is not 0. So we're searching for the solution for the system that is not 0. And that only exists, actually, the solution for this only exists if the matrix is not full rank. Right? So this is why, we know that the solution only is there if this matrix is not regular or if it's singular. And we know that for matrices that are not full rank, the determinant is 0. Right? So this is what we discussed before. We talked about the full rank assumption and the rank assumption of the regressor matrices X, and when we discussed the existence of the OLS estimator. And here we're actually going to use the opposite of this because we know that A minus lambda I isn't full rank. To find this non-zero, non-trivial solution X, we use that for a matrix that is not regular, the determinant of that matrix is actually 0. our example, let me just make sure that you see why this is important. The determinant, just as a reminder how to calculate this, the determinant of our matrix that we have here is the determinant of 2 minus lambda one, 2 minus lambda. And because it's a 2 by 2 matrix, we can calculate this determinant very easily by multiplying the main diagonal and subtracting from that the product of the off-diagonal elements. Right, so this is the determinant. And we know that that has to be 0. And now you see we have this polynomial equation with respect to lambda, and we can just solve this equation for the vectors. Right? So the determinant, and that's just what's here, the determinant of this term here is always going to be a polynomial of degree n, which is just the order of the matrix. And the solutions to this characteristic polynomial, if we set this polynomial to 0, are our eigenvectors, lambda. So if we want to calculate this, equations, which is mathematically. I think we all practice this in school a lot, to a large extent. So let's just now, people, I think, usually for us it's enough to know the eigenvalues, but I also just for completeness want to show you how to calculate the eigenvectors. And then I'm going to first go through the whole thing, but the eigenvectors are also the solution to a linear system of equations. Right? So in the end we can write it with the definition, we can see it in the definition. And we know that a x minus lambda I x is equal to 0, so that we have a minus lambda I x is equal to 0. So in the end we have this. What is this? Well, we have the value a11 minus lambda a12, a21, a22 minus lambda times x1, x2, and this is supposed to be 0, so you already see that this is a linear system of equations. So we have two equations with two unknowns. So we can calculate the solutions for x1 and x2. Okay, so what's happening here is we plug in all of the values. So we have 2 minus the eigenvalue, and let's just pick eigenvalue 3. So you can do this then for both eigenvalues. So the eigenvalue 3 and then 1, 1, 2 minus 3. So we get this system of equations, so that we solve kind of this thing here. And if you remember and want to do this, we can use the Gauss algorithm, where we produce a diagonal matrix on the left hand side, on the parameter matrix, in the coefficient matrix. And in this case it's very, very simple, because we just subtract the first equation from the second equation, so that we get this result. And there you go.
Where is the minus 3?
Sorry, which one?
Like, 2 minus 3 is minus 1.
Yes. Add them. Thanks. I looked at them wrong. Okay, so we add the first equation to the second equation, then we get this result that we have the second column is completely 0, and now, and this is why I don't want to go into this too detailed. Think about all of the knowledge on how to solve linear system of equations. If we get a zero line in here, that means that this system of equation has infinitely many solutions, right? Which is true because we do get a whole set of eigenvectors, but we can still think about the calculate, know something about the eigenvectors. And what we also see, what does this mean? That there's a zero here, well, the matrix is not full rank. And this is what we already discussed, what I discussed before, right? So this matrix A minus lambda I is not full rank. It's not a full rank matrix. It's not regular. So we are going to get this zero line here always. And then we just use this information. You now here see that the x minus x1 plus x2 is equal to 0 in the first equation. So we know that x1 is actually equal to x2. So all vectors that fulfill this x1 is equal to x2 are eigenvectors, right? And then we just pick out, usually we just pick out one specific eigenvector, so that the eigenvector x is, in this case, 1, 1. Or it's kind of, actually, it's all of the eigenvectors, it's 1, 1 times some factor s. Right? And you can do the same thing. So this is why kind of the math, this is what I meant before when I said the math behind how to get eigenvalues and eigenvectors isn't very hard, because all of this is, I don't want to say this point, but I mean, we all, in my school, when I went to school, I calculated a lot of roots of polynomials and I calculated a lot of solutions for a linear system of equations, right? So it's kind of school math. So this is why it's not so but the implication of the eigenvectors is actually then very interesting when it comes to how we can use them and what they tell us about the matrices and our models, our data, and so on. So this is why I wanted to show you this very quickly. And then I know the slides are way more. I know there's way more. I thought let's focus on how we actually get there. And if you want to go through them, I mean the next slides are really more examples, so more information for you. And if we would have had time, we could have gone through them all, but it doesn't. I mean, this is not the main focus of this course. So sad that we can't go through the whole thing. But yeah, I mean, and then a lot of properties and what to know about eigenvectors, right? So this is kind of and for example, here the first thing is the eigenvector values of the identity matrix are all 1, and the eigenvectors are actually you could calculate the eigenvectors of an identity matrix very easily. That's maybe for you as an exercise if you want to go into more detail with the eigenvectors, right? And then what's also very nice is if we have this diagonal matrix, then the eigenvalues are just the values on the main diagonal, which is very nice to say for triangular matrices. Yeah, so that's also great. So this is kind of some stuff. Then the eigenvector values, which is also maybe interesting or important, the eigenvalues of an invertible matrix A are then just also the inverse of the eigenvalues. Yeah, so, and here just some percent. I don't want to go through all of them, but you can go through them if you like on your own, if you want to. I mean, this is more math and not. Also the eigenvalues of a transpose, that's also maybe a nice thing. The eigenvalues of a transpose are the same as the eigenvalues of the original matrix, so the eigenvalues of A and A prime are the same, but the eigenvectors are different, which is also nice, interesting. So if we have the transpose, the eigenvalues are going to be the same. Yeah, this is actually, maybe we're going to come to this later on in the course, this is actually something, the eigenvalues of the symmetric matrix is actually something that is used in some methods, in some statistical methods, because it has such a nice, because covariance matrices are always symmetric, so we can use this deconstruction here. If we have a covariance matrix A, then we can deconstruct this into the invertible matrices of the eigenvectors and a matrix A with all of the and the matrix A, and get just a matrix, a diagonal matrix with only the eigenvalues on the main diagonals. And this is used in some of the statistical methods. This is why I left it on the slide. But let's see if we get to that. If you heard about the word principal components already, so this is kind of what's behind the principal component analysis, and it's used in machine learning also, feature selection, stuff like this. So this is all in a lot of cases. That's not that interesting. Yeah, it's more about the determinant. And here on the last slide, we get this result that the eigenvalues of a positive definite matrix are always positive. And how do we do this? I think the proof is pretty neat because we just start with the definition of eigenvalues and then rearrange it. So pre-multiply both sides with B prime to get this quadratic form that is in the definition of positive definiteness, and then we know that these are the same, and then we just know that the last thing here, if we have the lambda, which is a scalar, we can pull this in front of the multiplication, so in the end we get here the lambda times v prime v, and because this is a scalar product, which is just the sum of the squared main diagonal elements of the vector, so it's a sum of squared values, we know that this is always positive. If this v prime is always positive, we know that this is by construction positive, so for this whole thing to be positive, lambda has to be also positive. Yeah, it's kind of an neat little proof. And this is what Professor Knopf talked about in the lecture, kind of where I wanted to get. Okay. Are there any questions before we go?
Thank you.